Hello everyone, this is Miss Haneen Khair from Al Shumukh International School. This video is to help you understand the last topic in grade 12 syllabus, electrochemistry. We will start our topic by recalling the several definitions of oxidation and reduction. We can describe an oxidation reaction as addition of oxygen or loss of hydrogen or loss of electrons. In this topic mainly, we will consider the loss of electrons in defining oxidation. Similarly, we can define reduction in terms of loss of oxygen, adding hydrogen, or gaining electrons. Again, we are going to consider the electrons in defining reduction in electrochemistry. What are oxidizing and reducing agents? An oxidizing agent oxidizes other species, accepts electrons, so themselves are being reduced. So therefore, if you have an oxidizing agent, itself it's undergoing reduction, it's gaining electrons, and it's oxidizing other species. A reducing agent, on the other hand, reduces other species, itself undergoes oxidation and donates or loses electrons. For example, in the reaction below, NaCl plus F2 forming NaF plus Cl2. As you can see, Cl minus ions here are losing electrons and forming Cl2. So the Cl minus ions are undergoing oxidation. However, F2 molecules are gaining 2 electrons to form 2 F minus ions. So F2 is undergoing reduction. So Cl minus is the reducing agent, F2 is the oxidizing agent. So fluorine oxidizes Cl minus, it accepts the electrons from Cl minus, it is reduced to F minus, and it's acting as an oxidizing agent. Of course, the Na plus here is a spectator ion, so we don't have to worry about it. Losing and gaining electrons should happen at the same time. Each oxidation reaction should be accompanied by a reduction reaction. You can never have an oxidation without a reduction, or a reduction without the oxidation. And you have to be careful that the number of electrons lost and gained are equal. So the overall reaction that combines an oxidation and a reduction reaction is called a redox reaction. So as you can see here, Cl2 is gaining 2 electrons to form 2 Cl minus. This is reduction because electrons are gained, and Cl2 is oxidizing agent. Fe2 plus loses 1 more electron to form Fe3 plus. So Fe2 plus is undergoing oxidation and it's acting as a reducing agent. You have 2 electrons gained in the first half reaction, 1 electron lost in the second half reaction. Therefore, we need to balance the number of electrons by multiplying the second half reaction or the oxidation half reaction by 2. So now you have 2 electrons lost and 2 electrons gained. The overall reaction should not contain any electrons. Application. Each of the following equations involves a redox reaction. Study it, then answer the following questions. So you have CO2 plus reacting with zinc to form Zn2 plus and Cu. What is being oxidized? As you can see, zinc is losing the electrons, so therefore zinc is being oxidized, so Zn. What is being reduced? Cu2 plus is gaining 2 electrons from zinc, and forming Cu. So Cu2 plus is being reduced. Which is the oxidizing agent? The species that undergoes reduction is the oxidizing agent. So therefore, Cu2 plus is the oxidizing agent and zinc is the reducing agent. Another example, Cl2 reacting with Fe2 plus to form Cl minus and Fe3 plus. Cl2 is gaining 2 electrons to form 2 Cl minus. It's going from neutral to negative. So it's gaining 2 electrons. Fe2 plus is losing 1 more electron to form Fe3 plus. So Fe2 plus is being oxidized. It's acting as a reducing agent. And Cl2 is being reduced and it's acting as an oxidizing agent. Reactivity series. Metals can be listed in order of how reactive they are. This list is called the reactivity series. Of course, several experiments were carried out to identify the reactivity of a metal, to compare the metal's reactivity to each other. The more reactive the metal, the more vigorous the reaction is. So as you can see, K, potassium, is the most reactive metal among the ones mentioned in the list, and gold is the least reactive metal. So this is called reactivity series. The greater the reactivity of a metal, the greater its reducing power. Remember, reducing power is the ability of undergoing oxidation. So it's the ability of losing electrons. Metals do not gain electrons. Metals only lose electrons. So therefore, metals can undergo oxidation. However, metal ions can undergo reduction or oxidation depending on the ion itself, if it can form more than one oxidation state, as we saw in topic 1, transition metals. So as you can see here, potassium, we said it's the most reactive metal. So it has the greatest reducing power and it has the greatest tendency to ionize, to form ions, to undergo oxidation. However, Ag is the least reactive metal in this list. So therefore, it is the least in the ability to lose electrons or undergo oxidation. Now, the reducing power and the oxidizing power vary inversely. If a metal has a very high reducing power, the metal ion, on the other hand, will have very low oxidizing power. So if a metal can lose electrons really quickly, its metal ion can't gain electrons that quickly. So the most reactive ion is Ag+, the one that has the least reactive metal. So if a metal is very unreactive, its metal ion is going to be very reactive. If a metal is very reactive, its metal ion is more likely to be unreactive. Oxidizing power of the metal ion and reducing power of the metal vary inversely to each other. The H plus H2 couple. Whenever a metal reacts with an acid, H plus acts as an oxidizing agent and undergoes reduction to form hydrogen gas. Not all metals, however, react with acids. A metal that is below hydrogen will not react with dilute acid. So in this list, for example, copper cannot react with H plus. If you put copper with an acid, no reaction will be observed. Similarly, silver, similar to this, is gold as well. But any metal that is more reactive than H plus than H2, any metal that is more reactive than H2 will undergo a reaction with the H plus ion. Now, we're done recalling basic information that you have studied in previous years and related to electrochemistry. We are going to start by defining electrochemistry. I would like to bring your attention to the part of the syllabus that you're studying. It's 9.1.b, that's the specification. And the page number that you can find this information at is page 382 in your book. Alright, so electrochemistry deals with chemical reactions that produce electricity and the changes associated with the passage of electrical current. How to convert chemical energy to electrical energy, that's electrochemistry. Of course, the reactions involve electron transfer, therefore, we are dealing with redox reactions. The transfer of the electrons occur at electrodes. So we have basically two electrodes, as you will see, anode and cathode. On these electrodes, transfer of the electron occurs. Half cells. A half cell is one of the two electrodes in an electrochemical cell. So one cell is made up of two half cells. One will act as the anode, one will act as the cathode. So a half cell is one of these two half cells or one of these two electrodes. It is constructed by dipping a metal bar in an aqueous solution of the same metal ion. So if you want to construct a copper half cell, you have to dip the copper metal in a solution that contains Cu2 plus ions. You have to dip the metal in a solution of its own ion. So copper sulfate, CuSO4, contains Cu2 plus and SO4 minus. SO4 minus is a spectator ion, and Cu2 plus is the metal ion of the metal copper. As you can see, we have an equilibrium established here. So Cu is going to lose electrons to form Cu2 plus, and at the same time Cu2 plus present in the solution will gain the electrons to form back Cu. Basically, what determines which reaction is favored, backward or forward, depends on the other half cell present, and you are going to study it in further slides. So, an electrochemical cell is a device used to generate an electric current from a chemical reaction. It's constructed using two half cells. If you are using zinc half cell and copper half cell, we call it a Daniell cell, which is named after John Frederick Daniell, who is a British chemist who invented this cell in 1836. As you can see, zinc is dipped in a solution of Zn2+, copper is dipped in a solution of Cu2+. The two compartments are connected, so we have a closed circuit. The two electrodes are connected via wire, and the light or the lamp will light after the reaction starts. So the chemical reaction is converted to electrical energy. Now, oxidation and reduction. The metal with greater reducing power, that is the metal that is more reactive, that is the metal that is able to lose electrons more, is always placed at the anode, where oxidation takes place. So oxidation takes place at the anode, and we put the more reactive metal at the anode as well. The metal with lower reducing power is placed at the cathode, where reduction takes place at the cathode. So you have zinc and copper. Zinc is more reactive than copper, so therefore zinc is placed at the anode and it's losing the electrons. Copper is placed at the cathode and Cu2 plus ions are gaining the electrons. Cu metal can never gain electrons. It's the metal ion that will gain the electrons instead. The overall equation, as you can see, the number of electrons is balanced in the half reactions. 2 electrons are lost in oxidation, 2 electrons are gained in reduction. So you just have to cancel them out and add the reactants and the products. So Cu2 plus with zinc forms Zn2 plus with Cu. That's the total or overall reaction that is taking place in this electrochemical cell. Now, how the electrons flow in an electrochemical cell? As you might have predicted, electrons flow from the anode to the cathode. So as you can see, this is the anode, the one or the most reactive metal. The metal with the more reducing power is placed at the anode, and the electrons will go from the anode to the cathode. Now, once the electrons are moving in one direction, the current will move in the opposite direction. So the current will flow from the cathode to the anode. Now, we are going to talk about salt bridge. We have two types of salt bridges. We have the filter paper soaked in electrolyte, so you can get any filter paper, just soak it in the electrolyte. Electrolytes is a solution of ions, and then put it in the two compartments. What's the role of the salt bridge? We want to connect the cell. If the cell is an open circuit, then electrons can't flow, so it just completes the circuit. The other type of the salt bridge is a bent tube, which is packed with jelly electrolytes, and as you can see at the end, it's plugged with porous plugs. The porous plugs at the end of the bent tube salt bridge allow ions to flow while minimizing the mixing of the electrolytes by diffusion. So if you're using, for example, potassium nitrate, the jelly potassium nitrate will be inside the bent tube salt bridge. The electrolytes are not going to diffuse out from the salt bridge because of these porous plugs. As you can see, it's labeled here. Now, what are the electrolytes that we can use? The salt bridge can contain any ionic salt as long as these ions do not interfere with the components of the half cells. To be on the safe side, we use potassium or sodium nitrates because you know that potassium ions are always soluble. Sodium ions and nitrate ions are always soluble, they do not precipitate. So ideally, those are the best electrolytes to use in a salt bridge. So as you can see in this diagram, you have Cu and Ag. Cu is more reactive than Ag, so Cu is placed at the anode and Ag is placed at the cathode. Electrons are flowing from the anode to the cathode. The anode and the cathode are connected via wires, using wires, and those wires are connected to a voltmeter to measure how much energy or how much electricity is passing. The two compartments, the two beakers, are connected using a salt bridge that contains KNO3, potassium nitrate. What are the roles of the salt bridge? The salt bridge is necessary, as we said before, to complete the electrical circuit. Not only that, it preserves the electroneutrality of the cell. At the anode, and when oxidation of the metal takes place, the concentration of the cations will increase. So therefore, to make or to neutralize this extra cations formed, the anions of the salt bridge migrate to the anode compartments. At the cathode, what happens is reduction, where the metal ion gains electrons and form the metal. So therefore, the amount of the cations at the cathode decrease. And this is again neutralized by the migration of the cation of the salt bridge to the cathode compartment. Summing up what we studied before, as you can see, this is the cathode, this is the anode. It's not necessary that always the anode is placed at the left-hand side, as you notice. But what you need to know is that electrons always go from the anode to the cathode. What's happening here is that the amount of the cations at the cathode is decreasing once the reaction starts. So what's going to happen, more cations will be supplied from the salt bridge. At the anode, the amount of the cations will increase. So what's going to happen, more anions will be provided from the salt bridge. Electromotive force, or EMF, and the voltmeter to be used will be discussed in this slide. The electromotive force is the measured potential difference of a cell when no current is flowing. So it's the difference in the potentials of the two electrodes when no current is flowing. To draw off any current flowing, we will use a high resistance voltmeter. If you are using a high resistance voltmeter, or the role of using The aim of using a high resistance voltmeter is to ensure that there is no current is flowing when you are measuring the EMF. When you want to measure the EMF or the potential difference between electrodes, you have to make sure that you are using a high resistance voltmeter that draws off any current. The value read on the voltmeter represents the difference in the potential between the two half cells when both reactions are at equilibrium. For example, we have this cell constructed from copper and Ag. As you notice, Cu is on the anode, is at the anode, Ag is at the cathode. The electrodes are connected using wires, so the metal strips are the electrodes. The beakers or the compartments are connected using a salt bridge containing NaNO3. When the circuit is complete, the voltmeter, the high resistance voltmeter, is going to measure the potential difference between Cu and Ag, and it's going to be plus 0.46. Now, if by mistake Ag was placed at the anode and Cu was placed at the cathode, they are swapped, then the voltmeter will read the same reading but with the opposite sign. So then the voltmeter will read negative 0.46 volts. A negative value read on the voltmeter indicates that the metal electrode is negative with respect to the hydrogen electrode. The hydrogen electrode is the standard electrode to which we compare all other metals. There are certain conditions and certain standard conditions that we will explain in other videos. But for now, you can think that the hydrogen electrode is just a reference electrode. If the voltmeter gives you a negative value compared to the hydrogen electrode, this means that the metal is negative with respect to H2. So therefore the metal is more reactive than H2, and it should be placed at the anode instead of H2. A positive value read on the voltmeter indicates that the metal electrode is positive with respect to the hydrogen electrode. So if you are placing hydrogen gas and the voltmeter is reading a positive value, this means that the hydrogen has more, or the hydrogen is more reactive than the metal that you are measuring. In this case, H2 is more reactive than Cu. That's why the voltmeter is reading a positive value. And the electrons are flowing from the anode to the cathode. Now, that's everything that we studied so far. You have electrochemical cell. It's made from two compartments. In this case, I'm studying Daniell cell, zinc and copper. Zinc is more reactive than copper. It has a greater reducing power. So I'm gonna put zinc at the negative electrode or at the anode, and copper at the positive electrode or at the cathode. Both electrodes are connected to a switch and a voltmeter using wires. The two compartments or half cells are connected using a bent tubed salt bridge containing NaNO3 electrolytes. Zinc electrode is dipped in a solution of the zinc ion. Cu electrode is dipped in a solution of Cu2 plus ions. Oxidation will take place at the anode. Electrons will move from the anode to the cathode using the wires. Oxidation half reaction is written just below the zinc half cell. Zn is losing 2 electrons to form Zn2 plus. Cu2 plus 2 electrons forming Cu. This is the half reaction occurring at the cathode, where Cu2 plus ions are reduced to copper. At the anode, the amount of Zn2 plus ions is going to increase, whereas at the cathode, the concentration of cations is going to decrease. This is compensated by the movement of the ions from the salt bridge. Cations go to the cathode to neutralize the compartment, and anions go to the anode to neutralize the extra or the excess concentration of the cations. Thank you for watching.